Welcome. This video is a discussion of how to use integration to find surface areas. We're going to imagine taking a two-dimensional graph and spinning it around an axis, similar to how we find volumes of revolution. Since it's hard to write this in 2 dimensions, let's take a look at this in 3D. Here we have a two-dimensional curve, and we're going to imagine taking this curve and spinning it about the x-axis. This gives us a 3-dimensional solid. In this case, it looks a little bit like a lampshade. We would like to find the areas of solids like this. How much material is being used for the area of this rotated solid? There are 2 cases that we'll take a look at. We'll think about rotating about the x-axis or about the y-axis, and we have these 2 formulas. In both of these formulas, we're using dl. This is the same dl that we had with arc length. We can have dl in terms of a dx or in terms of dy, depending on how we want to integrate. Whether we're rotating about the x-axis or the y-axis determines if we have an x or a y in this expression. Let's take a look at where this formula comes from. This won't be a rigorous proof, but it should give us an intuitive idea. Imagine taking some curve and spinning that curve, in this case, about the x-axis. And let's take a thin slice of that solid and think about the area of that thin slice that's been spun around. This has some distance along the curve, and let's call this distance dl, just as we did for arc length. If we take that small cylinder and examine it closely, then this dl is the height of the cylinder. The cylinder has a radius which is equal to this distance here, and let's just call this y. It's some height y. So it has a radius of y. The area of this thin cylinder is just a small value of area. Let's call that dA. dA is the surface area of this cylinder. Surface area is the circumference times the height. The circumference is 2 times pi times the radius. So we have circumference times the height, which is dl. That's the value of the area of this small slice. To get the total surface area, we integrate or add up all of those small bits of area. We integrate dA. So this is 2 pi y dl. Once again, this is for rotation around the x-axis. If we rotated about the y-axis, we would have a similar expression, except we would have an x instead of a y. Now that we have an idea of where this formula comes from, let's practice applying it. We want to set up an integral to describe the surface area of this curve, and we'll rotate about the x-axis and about the y-axis. So imagine taking the curve y equals x squared, first of all, rotated about the x-axis. Here's the formula. It's been partially set up for us. This expression, once again, this is dl, the same dl that we had for arc length. And we could choose to write this in terms of x or in terms of y, regardless of which axis we rotate about. In this case, for this problem, it's easier to work in terms of x. So our integral becomes the integral of 2 pi, and now everything should be in terms of x. So instead of having y, we want to write this y in terms of x. For this curve, the relation between y and x is y equals x squared. So we replace the y with x squared so that the integral is expressed completely in terms of x. Then we have 1 plus dy over dx. Well, dy over dx is the derivative of x squared. So in this case, dy over dx is 2x. So we have 1 plus 2x squared dx. We're integrating with respect to x. So the limits of integration will be these x values from 0 to 2. This integral describes the surface area of this curve rotated about the x-axis. What happens if we want to rotate about the y-axis? Well, here's the formula. It's very similar, except instead of having a y, we have an x here. The dy over dx is the same, and the limits of integration are the same. So this surface area is 2 pi x, and now since everything's in terms of x, we don't have to replace this x, it just remains x. And then this square root is 1 plus 2x, quantity squared, dx. We're integrating once again from 0 to 2.